Our investigation actually found out a way to keep the magnet the same distance the entire time. So I've placed two books on both sides to hold up a glass Tupperware container, and on the bottom of this container I will be taping the magnet that we're using to test, and then I will line up directly over this magnet that is taped down to the scale so that we can use it to measure the force without Mr. Yang's shaky hands. For our diameter size experiment, there are 5 magnets from 0.5 centimeters, 0.75 centimeters, 1 centimeters, 1.25, and 1.5 centimeter diameter magnets. We'll actually be focusing on these 4, 0.75 through 1.5, with the smallest one as a bonus if you guys want to graph this to go above and beyond. And look at it, it is very small and very cute. All right, and I will be taping this to the bottom of the glass container and holding it directly over the scale to find out the force that it makes on the bottom magnet. All right, we'll begin with the 1.5 centimeter. Okay, 1.5 centimeters is 10 grams of force. 1.25 centimeters at 8 grams of force. 1 centimeter is at 6 grams of force. 0.75 centimeters at 4 grams of force. And lastly, 0.5 centimeters, this is the bonus, at 3 grams of force. For the thickness of magnets investigation, we have 4 different magnets. Now, in reality, these are the same magnets, each of them 2 millimeters thick, and I just stacked them at different number of stacks. So the first one is just a single magnet, 2 millimeters. The second one is 2 magnets stacked on top of each other at 4 millimeters. Third one is 3 magnets together at 6 millimeters. And last one is 4 magnets stacked together at 8 millimeters in thickness. And they are the same width and just on different thicknesses. We will begin with a 2 millimeter magnet at a force of 5 grams. 4 millimeter magnet at a force of 14 grams. 6 millimeter magnet at 17 grams of force. 8 millimeter magnet finally at 22 grams of force. The thing to note is that as I am increasing the thickness of the magnet that is taped down onto the top here, I'm also increasing the height of the glass container from the bottom magnet, because I want to maintain this distance between the top magnet and the magnet taped down to the scale to be the same in all 4 different magnet thickness I'm testing. So I need to raise the height of the glass container, and I did that by actually just putting these other magnets under here. So each of these magnets that I bought are all 2 millimeters. So for the first test that I've done with a 2 millimeter magnet, I didn't put anything under the glass container. And then with the 4 millimeter magnet, I added one of these discs under each side of the glass containers to raise the glass container's height by 2 millimeters. And then for the 6, I added a second magnet to hold the height up of the glass container. And then for the 8th one just now, I placed 3 2 millimeters thick round magnets. So in total, we're raising the height by 6 centimeters, so that the height difference between the top and bottom magnet is the same as when there was only one magnet taped to the top to the bottom. This is our diameter of the coil investigation. So we have one coil at 2 centimeters in diameter, approximately 2 centimeters, one coil at 3 centimeters in diameter, and one at 5 centimeters in diameter. And for this one, I've chosen to use this phone holder, which has this claw to hold the coil over this disc magnet on the scale to read the reading. And for the battery, we'll be using these 4 AA batteries connected together for the diameter experiment. Let's begin. We will begin with our 5 centimeter coil, and you can see that it is not touching the scale. And the 5 centimeter has a force of 3 grams. Next up, we have 3 cm coil with a force of 6 grams. Oh, this is surprising because it's actually smaller, but with a bigger force. Finally, we have the 2 cm coil. You see it is not touching the scale with a force of 9 grams. Interesting. So in this case, smaller is not weaker, but rather stronger. Next up is our investigation of number of turns. We have 3 different coil of wires. First with 25 turns, then 50 turns, and then coil with 75 turns. I made them approximately the same diameter as well. And we're going to be holding that up with a phone holder / claw over the magnet tape down on the scale to measure the force. Let's begin. We will begin with the 25 turns coil, and the power will be provided by 4 AA batteries. So 25 turns will produce a force of 4 grams. Next up, we have the coil, which is 50 turns, which produces a force of 7 grams. Finally, we have our coil of 75 turns, which produces a force of 9 grams. So not as dramatic as I thought, honestly, but it has been, forces did increase along with the number of turns. The last experiment of the number of currents going through the coil, we will be using the same coil, which is I think approximately 3 diameter coil with 50 turns, and then I'll be connecting it with just 1 battery, then 2 batteries, then 3 batteries, then 4 batteries together, and then measuring the amount of force you will place on the scale while it's being held up by the phone holder / claw. Let's begin by testing 1 battery, which has a force of 8 grams. Next, we have 2 batteries with a force of 8 grams. 9 grams. 2 batteries, 9 grams. Let's call it that. We have 3 batteries at a force of 11 grams. So with 4 batteries, I'm using my little battery holder here. We have a force of 11 grams still. So interesting. I wonder why still 11 grams, even though we're using 4 batteries.